Hello, and welcome to the short ISP. This is the SHIB 181, a discrete logic ALU recreated after the 74181 from the 1970s. The SHIB 181 has 16 logic functions and 16 arithmetic functions divided into two, therefore it actually has 32 arithmetic functions, as the table shows. Now, there seems to be quite a bit of odd stuff happening here. You see to have odd functions such as f equals a or b plus a plus 1. Where does that get created and why is that useful? Well, firstly, the logic functions are the 16 possible Boolean functions. There are 16 possible Boolean functions because if the function f of a and b has 1-bit inputs, then there are 4 rows to the truth table. Therefore, when extended from 2 to 4 bits, there's exactly 2 to the 4, or 16 logic functions for the ALU. The 16 functions are selected by the S0 and S3 inputs. Secondly, the arithmetic functions are a combination of addition, subtraction, logic operations. Although there are some strange ones, such as a plus ab plus 1. How does that get created? Well, despite their seemingly irrational behavior, there is a rational system behind them. The way it works is that all the arithmetic functions are simply a plus a logic function plus the carry in. For example, if the logic function equals b, then the arithmetic operation will be a plus b plus the carry in. Now, this works quite well. However, if you look at the table, it doesn't really work. That's because the Boolean functions are in a different order than the arithmetic functions. This will be discussed in the next section, discussing the logic diagram that can generate this entire truth table. Because the arithmetic functions are just the addition of 3 values, an adder can be used to solve the solutions of the arithmetic functions. The simplest but most inefficient way to construct an adder is to use a 1-bit full adder for each bit, with the carry out going to the adder to the next adder. For reference, this has been discussed 2 years ago, during my ISP of that year. Now, this type of addition is called a ripple carry. It makes addition a serial operation instead of a parallel one, slowing the ALU. Now, this is pretty bad. It means it requires 2 clock pulses to have it work. The way this is solved is by using something called carry look-ahead. Carry look-ahead uses generate and propagate control lines to determine if each bit addition will always generate a carry or can potentially generate a carry. For instance, if the ALU is adding 0 plus 0 plus the carry, well, there's no chance that there's carry out from that. Now, if it's 1 plus 1 plus carry, there will always be a carry out from that. And then if it's 0 plus 1 plus carry, it's only going to carry out if there is a carry in. Now, this is what's shown by the top section of the logic diagram. All of these, when it repeats 4 times, are what control the carries. Now, in the bottom section is what the actual addition is. If you think back to the adders, it's just an XOR gate with a carry in. Since we've calculated the carry in, it's just an XOR gate, thus simplifying it to an incredibly simple one-step process. Since the SHIB 181 is functionally identical to the 74181, it can work within the chump. Here it is calculating Feinberg's code. The top line here are the A inputs, followed by the B inputs below it, then S, and the F outputs. The leftmost red are the various signals coming out. The top right, or the yellow, is the G part of the internal. Below that is green, that's the P, and the other ones are various other internal signals. The board is comprised of 2 separate ones, actually. The top one's a display, and the bottom one's just the simple logic. They can function independent from one each other. See? It's still calculating, but the display's been turned off. Thanks for watching. This project has taken me 5 months, and I couldn't be more satisfied with it. I can't wait for the rest of the opportunities the ACES program will give me. If this is my last year, I'm going to make the best out of it. Thank you.